the Astronomical Society of Botswana. I would like to introduce Harold Hester. He really needs no introduction. He has been doing this introduction to the night sky for the coming month, for the past, I don't know, 1 year or two. And now we are kickstarting 2024 with this presentation of the February night sky. So I think I'll hand over to Harold for his presentation. Over to you, Harold.
Thank you very much for that introduction, Prof. So let's go right into it. I'm at a bit of a disadvantage because I haven't got the book by Will Tyrion of the stars of the night sky 2024. But fortunately, the stars in February 2024 are exactly the same as the stars in 2023. So I was able to use last year's book. The only thing that's changed is the planets. So you'll have to see if I make any typographical errors. Right, so let's move on. When you go stargazing, there are three things you need to look for. One is in summer, the Milky Way and Orion. In winter, of course, instead of Orion, we look for Scorpio. The other is the zodiacal line or the ecliptic. And with the 12 zodiac signs, constellations on that. And now I've listed them all. The ones that we can see at present are starting from the west, Pisces, Aries, as I've mentioned there. And I presume you can all read those, up to Libra in the east. So once you've got those, once you've got the ecliptic and you can place those constellations on the ecliptic, you know where Orion is, then you can orientate yourself and take it from there. So some easy to identify bright stars at the moment are Rigel and Betelgeuse in Orion. Procyon is the yellowish white star in Canis Minor. That's below to the right of Orion. Sirius, the brightest star in the night sky, located in Canis Major. I've mentioned Antares, red supergiant in Scorpius. That comes on just before dawn, when Scorpius comes up. Spica is the brightest bluish white star in Virgo. There's Canopus, Regulus, and the pointers, Alpha and Beta Centauri. I'm just mentioning those quickly. Those are the ones to look for straight away, and then you know where you are. Planet visibility. Now, this is coming quite interesting. Venus we see in the morning, and the best time in this year will be up until the February the 11th. Mars is barely visible, but it's close to Mercury, and I'll talk about that a little bit later. Jupiter is brilliant near the stars of the constellation Aries in the evening sky, and Saturn is visible near the stars of the constellation Aquarius in the evening sky, but that goes down during the night. Now, on Saturday morning, if you look southeast, you will see Mercury and Mars are very, very close together, very close. But they are low down, just above the horizon. So if you've got a mountain in your way, you won't see them. But that's something to look forward to. That's this Saturday morning, and Venus is above them. I've got there January 2024, but it's the same applies to February, virtually. Saturn is moving towards the west near Fomalhaut, also low down in the sky. Now, there's the normal map which we show, highlighting in red the major stars, which you can see at the moment. This is looking south. Crux and the two pointers are there. Spica is very close to the eastern horizon. It's in Virgo. Canopus, as usual, dominating the sky in Carina. Sirius, you can see right at the top of this map in Canis Major. And then Achernar down near the southwest. Okay. So then going to the next map that's looking north, we see Orion. That's Orion. That's our pivot. That's what we're looking at. Aldebaran below that to the left. Sirius again. Regulus to the right towards the eastern horizon. The two Gemini twins, Pollux and Castor, just above the northern horizon. And I'm going to come later to the ghost of Jupiter. It's in Hydra, and talk about that. And then Canopus up in, we've talked about that in Carina. So in the early evening in February, I mentioned all these stars and constellations. Orion and Sirius are high overhead. Aldebaran in Taurus in the west. Achernar and Canopus are prominent in the south, and Crux is low in the southeast. Those are all very easy to see. Midnight sky, I mentioned those stars and constellations. Pre-dawn, I've just mentioned the planets. I haven't mentioned the different constellations. But those are what you can see. It's easy to see. Again, I say easy to see. So most of these you could probably see from Gaborone with all its light pollution, but it really is better to go away from Gaborone into the desert and appreciate the magnificent night sky that we enjoy here in Botswana. Now, this is rather an interesting diagram where Orion is the center of what's happening up in the sky above us. And you can see the various lines I've drawn. Look at the top, going to the one from Rigel going up to Achernar, the other one pointing to Canopus. There's a little bit of artistic license taking the line from Betelgeuse through Sirius up to the false cross. It does bend a little bit. And then down to the right, we've got from Bellatrix through Betelgeuse down to Regulus, and then down to Pollux and Castor, the line, and then another line through Elnath to Capella, and lastly from Bellatrix through Aldebaran to Pleiades. The summer triangle is prominent at the moment, where you join lines Sirius to Procyon and Betelgeuse, and that's very easy to see at the moment. Right, I just want to talk about the ghost of Jupiter, which I only spotted doing some homework. The planetary nebula is most frequently called ghost of Jupiter due to its similar shape to the planet. And the two ends of the nebula are marked by flyers. They're lobes of fast-moving gas. So I thought that was quite interesting. It goes under NGC 3242. And it's located in the constellation of Hydra. So find Hydra, and then you'll see this. It's best to look through a telescope. I don't think you certainly won't see it with the naked eye. But I thought that was something different to talk about. And that's the rest of my story. It's over to the main speaker.
Oh, thank you very much. I don't know whether maybe we've got a question or two from the audience, from the. Okay, it looks like, yes, I think over to the main speaker. So I would let Mike make the introductions.
Thank you. Okay. Thank you very much, Harold, for your very interesting monthly talk. And thanks also to Dr. Schipper for setting up this link at the last minute. I'm Mike Bode. As you can tell by my jumper, I'm actually in the Northern Hemisphere as well as our speaker tonight. I'm near Liverpool, but I'm visiting Prof in Botswana at Buist. So we're very pleased to welcome Roberto Orosei, who did his undergraduate work at the University of Bologna, then a PhD at the University of Rome, La Sapienza. He was a research fellow at ESA at ESTEC in Noordwijk, and then at the Institute of Space Astrophysics, also in Rome. He's been involved in a host of solar system missions for both the European Space Agency and for NASA. He's, for example, the PI of the MASIS radar aboard ESA's Mars Express spacecraft. And he's currently at the Institute for Radio Astronomy in Bologna and lectures in exobiology at the University of Bologna. So from this, you could tell that there's hardly anyone more fitting to give the talk tonight, the search for life in the solar system. And so it's with great pleasure that I welcome our speaker tonight, Roberto. Thank you.
Thank you very much. Thank you very much, and thank you for having me today. And so what I would be presenting in the next 45 minutes or so is a brief summary of the basic concepts that are applied in the search for life outside the Earth, which requires some introduction, I believe. I'm not sure how familiar you are with this kind of themes. I understand that people attending this conference come from different backgrounds. So actually searching for life for astronomers and planetary scientists is something that has to do with the search for the physical parameters that limit the possibility for life to exist. And in general, the word we use is habitability, because before detecting life, before knowing if we are seeing something that is living outside the Earth, we need to define where life is expected to be found. And this is a big issue because we have no idea, no experience of what life could be if it outside the Earth. We do not know its chemistry, basic fundamentals, but there are, let's say, basic assumptions based on fundamental chemistry, the stability of molecules that are necessary, the complex molecules that are necessary to perform the complex reactions taking place continuously inside the living organism. And based on these assumptions and our limited knowledge of, the only knowledge we have is life on Earth, we usually define the search for life starting from the search for habitability. And habitability is defined by essentially four main criteria. One is the availability for life, for chemical reactions that would lead to life, of the most common chemical elements that are present in living organisms, specifically carbon, hydrogen, nitrogen, oxygen, phosphorus, and so forth. Also, a solvent is deemed to be necessary because chemistry within living organisms is extremely complex. It involves large molecules that will be solid at room temperatures. So for these molecules to be able to interact with each other, a solvent is required, allowing their motion, their movement through space. And another important and fundamental factor is the presence of energy of some kind. And of course, animals take their energy from organic matter produced by either other animals or plants. But plants themselves are able to process solar energy to produce organic compounds. So there is a fundamental need for energy to be present so that living organisms might exploit it for their own internal metabolism. And this can be, for Earth, the obvious form is solar energy, but indeed on Earth there are habitats, places where microorganisms live, where the sun doesn't shine, And for example, the energy for life is taken from maybe thermal energy for volcanic activity and other forms of chemical energy. And then there is a number of physicochemical conditions which are variable depending on the kind of organism you are considering. There are microorganisms that are able to live at temperatures below 0 centigrade or above 90 centigrade. And there are other organisms, very simple ones, that are capable of surviving or actually thriving in places where more complex life forms would die. So in general, this is a bit vague, but it's, let's say, considered one factor that could be assessed and should be assessed perhaps after the main three categories of chemical abundances, energy, and solvent are assessed. The advantage of these criteria is that they are quantitatively measurable and they can be observed from outside the planet, from Earth or from space, from a spacecraft orbiting another planet. So this is the criteria. These are the criteria through which we establish or try to establish if a planet or part of a planet is habitable. So in principle, it's capable of sustaining life as we know it. Now, it's also understood that habitability means different things in different circumstances. And we do not yet know how life actually emerged from a world where life did not exist in the early phases of the evolution of the Earth. But it's commonly understood and assumed that those conditions that were necessary and allowed the emergence of life were more restrictive than the ones that allow the presence of life on Earth today, in the sense that evolution has led many different life forms to develop and adapt to habitats that would have been not incapable of conducting to life as we see it today, I mean, to the other forms of life. So habitability is the key, the first thing that spacecraft instruments can measure. And moving forward, habitability, of course, does not imply life. So, the focus, I mean, much time during this conversation would be devoted to talk about Mars, which is the closest planet to Earth, or the second closest actually, but it's the most easily reachable by rockets, or let's say, because of the gravity pull of the sun becomes weaker as we move away from the sun. And Mars is a candidate planet for having hosted life, and perhaps even hosting it today. And the exploration of Mars is now driven by the search of habitable environment, either past or present. But this alone does not guarantee that we find life. We could have Mars that, in spite of the evidence, was never habitable for reasons that we would eventually discover or could eventually discover, or that was habitable but never developed life. So the exploration and the search for life is a complex endeavor that has to deal with many, many unknowns. And in particular, what we can measure is not enough information to tell us how the story of life actually unfolded on a different planet. Now, to establish if the planet is habitable, a planet like the Earth, a planet where the sun shines on the surface and the temperature due to the solar heating is enough to keep water molten liquid, so not freezing, not evaporating. Now, starts with defining the characteristics of the star around which a planet is orbiting. And the general, let's say, criterion, the first basic criterion to establish if a planet can be potentially habitable in the solar system or elsewhere is the so-called habitable zone, which is sometimes jokingly called the Goldilocks zone. So the range of distances from star in which surface temperature of planetary body is not neither too cold nor too hot. And as you can see in this graph, the Earth is, well, conveniently sitting just across in the middle of the habitable zone for the sun, for a star like the sun. The Mars is barely making it, and Venus, unfortunately, is just outside. Venus is too close to the sun, it's too hot. And in fact, we will briefly discuss how things were different in the past. Now, also maintaining habitability over a long time requires a number of factors that are seldom discussed when talking about life outside the Earth, and which have a complex interplay with each other. And just to briefly mention all these complicated set of interactions and feedbacks between factors, the mass of the planet determines much of its geological evolution, of course, also its chemical makeup, but the mass is key in determining if for example, an atmosphere can be maintained over time. It's not lost, for example, like in planets that are too small to withhold an atmosphere, and also is a key to understand how long it will keep evolving from the geological point of view. Volcanism is an important factor in determining the habitability, both because of the gas release from the interior of the planet to the atmosphere, and also for a number of phenomena that are related to life, like, for example, the possibility for life to develop in the first place as one of the environments that is now suspected of being the first site in which life developed on Earth is, in fact, the site of underwater volcanic activities, black smokers, as they are called. So not volcanoes really, or very small ones, but vents of hydrothermal activity where water was at a constant temperature, constantly hot or warm, and if you move away from it, and chemical elements were abundant because they were brought into the ocean water or seawater by the hot water coming from below. Also, star type, for example, is important because stars live for a longer or shorter life depending on their type. Stars like the sun will keep shining like they do today by burning hydrogen in their cores and producing helium for perhaps 10 billion years. But larger stars burn their fuel much more quickly, and the largest stars can survive only for tens of millions of years before running out of fuel and entering evolutionary phases that are highly destructive, like a supernova, and thus meaning spelling the end of any planet that could have been habitable and where life could have started developing. Again, 10 million years is a very short time compared to what we know of the origin of life on Earth, which required apparently a time of the order of 100 million years, so 10 times as much. The orbital characteristics, of course, mean for the habitable zone to be important, and of course, a very elliptical orbit would bring a planet in and out of the habitable zone, making for a very, very difficult environment for life to develop. Presence of the moon is also an influence. For example, our moon stabilizes the nutation of the axis of rotation of the planet, of our planet, in which in itself prevents extremes in tilt, spin axis inclination, which would lead to extremes in climate. And of course, in the history of Earth, impact events such as the one that caused the extinction of the dinosaurs in 65 million years ago have a key role in determining the continuous habitability of a planet. And atmospheric composition, of course, is key, as you can imagine. Magnetic field is important. It is often underestimated, but the magnetic field of Earth protects our atmosphere from erosion by the solar wind, the constant flux of charged particles being continuously irradiated by the sun. Those particles would tend to drag away slowly but inexorably our atmosphere over the course of time, and would leave us without an atmosphere. And this is the case for Mars, or a very much thinner atmosphere, as we will see. Plate tectonics is often underestimated, but it's key as for regulating the presence of CO2 in the atmosphere, and thus the balance of greenhouse gases and effects. This is a negative feedback cycle. CO2 is, of course, causing greenhouse warming, as we unfortunately are facing, are learning, and CO2 is soluble in rain, could be sent to the ground, and by making water slightly acidic would help in, for example, dissolving minerals of calcium, which would be then going entering the ocean through rivers and other waterways, and eventually deposit in the bottom of the sea as carbonate. Now, carbonates would then subduct and reach the mantle, and there they would decompose again and form again CO2, which would be erupted by volcanic activity. Now, the interesting factor that people seldom consider is that warming increase could be caused by an increase of CO2, but warming also causes an increase of the solubility of CO2 in water, thus sequestering much greater quantities of CO2 and then tending to decrease the quantity of CO2 in the atmosphere and thus lowering the greenhouse effect. And the other way around, if the climate gets colder for some reason, that would also lower the solubility of CO2 and then lead to a smaller rate of sequestration of CO2 from the atmosphere, and then increase the relative concentration of CO2, leading to more marked greenhouse effect and raising temperatures. This is the mechanism that has maintained the Earth habitable over long periods of time, over billions of years. This self-regulating cycle. Of course, there have been moments of hiccups and other accidents disrupting this cycle, but this is a key factor in maintaining life habitable. Now, if we look at the rest of the solar system, and which is schematically represented here, the planets are approximately to scale, so is the sun that we see on the left, but distances, of course, are not real, are not proportional to the size of the planet. Now, we start by not looking at giant planets. Jupiter, Saturn, Uranus, and Neptune are planets which are surrounded by very dense, very heavy shells of hydrogen, helium, and in some cases also methane and other gases. And whatever might be existing there, it's debatable. It's not the kind of life we would be expecting. And in fact, it's something people seldom ever consider the giant planets, the gas giants, as possibly inhabitable. However, their satellites, their moons, could be, and we will come to that. But for the time being, let's focus on the terrestrial rocky planets, those who are more similar to the Earth: Mercury, Venus, and Mars. Now, these three planets have been now explored to some extent, and in some cases extensively, especially in the case of Mars. And we already, let's say, we generally have a way to assess their habitability. Mercury is not considered habitable. It does not have an atmosphere. It does not have water on its surface. The surface temperature is way too high for water to be stable. So Mercury is not really the focus for the search of life. But Venus has its history of its own. Venus is physically the twin planet of the Earth. It has a very similar radius and mass, and yet at the same time, its atmosphere is 90 times denser at the surface than that of the Earth. It's all made of CO2. Its surface temperature is above the melting point of tin at around 700 kelvins due to a hugely strong greenhouse effect caused by the very dense atmosphere. There are clouds of sulfuric acid, so acid is raining on Venus. And so this place, which physically it's so similar to the Earth, is from the climatic point of view, from the habitability point of view, a sort of hell. Now, at the same time, there is a growing evidence that Venus in the past was different, and that could have been inhabitable, and that catastrophic greenhouse warming led Venus to become what it has become today. Now, in the early phases of the solar system, the sun was shining only at 70% its current brightness. The sun is gradually increasing its luminosity as it burns the hydrogen in its core and starts burning helium. And so the weaker sun of the past could have led to milder temperature on Venus. Also, there's evidence that Venus once possessed much more water than it has today. This has been based on the analysis of the very little water vapor remaining in its atmosphere today, which has a very high concentration of deuterated water. This is a bit technical. I don't know how deeply into details I can go about this, but essentially this means that having high concentration of heavy water means that probably the concentration of heavy water in the past was just like the one on Earth, but the preferential removal of lighter molecules, not the heavy water, but the normal water, due to loss to space, led to the increased concentration. And if you extrapolate back in time the quantity of water that should have been lost, then you get that you obtain that Venus should have had a substantial amount of water in its path. So, of course, the increasing luminosity of the sun, and the sun will keep growing its luminosity. So in the future, also the Earth will face and fade, but we are talking about 100 millions of years from now, led to the heating of the surface of Venus, and then eventually to the sublimation of water, which is also water vapor, a greenhouse gas, to the point in which that started to reaching temperatures in which also carbonated dissociated CO2 formed from the decomposition of water by ultraviolet radiation, and this led to the runaway greenhouse effect. Now, what was the starting event for this catastrophic development of Venusian climate? Apparently, it's the only geological difference, the main geological difference between Earth and Venus. Earth possesses plate tectonics, which removes CO2 from the atmosphere. Venus doesn't. So it's not clear why this happens. Perhaps the lower quantity of water in its crust makes it more rigid, less plastic, less liable to move and fold. But eventually, the crust of Venus becomes a rigid lid, and the heat from the interior that moves toward the surface through convection does not find a way to be released through volcanic activity, and eventually it erodes the crust up to the point in which there is widespread eruptions of lava across the planet, which last maybe hundreds of millions of years, certainly tens of millions of years, which form a new crust. Essentially, the entire planet is covered by lava flows and is resurfaced in a simple event. So this absence of a system of removing CO2 from the surface and from the atmosphere and dissipating heat from the interior was apparently the cause of the catastrophic evolution of the climate of Venus. However, it's still controversial, but phosphine has been detected in the atmosphere of Venus, and this molecule does not apparently have a obvious chemical pathway for its production. So it's suspected, but this is again very much debated, very controversial, that there could be a possible bacteria, some very primitive life forms existing in the high atmosphere of Venus above the cloud of acid, luckily for them, and producing phosphine. So this is Venus. And if we move to Mars, Mars also is a terrestrial planet, which is very similar to Earth. If I were not to say that this is a picture taken on Mars by a rover, you would perhaps think this is a terrestrial desert. And in fact, this image is almost natural color. The light or the sunlight on Mars has a more tan, brownish shade because of the dust which is suspended in the atmosphere, very light dust. So this image has been balanced so that this extra brownish hue has been removed. And so you would see a very familiar landscape, except for the lack of vegetation, but certainly there are areas on Earth that look like this. Now, also, beyond being a very arid and cold desert, because Mars is farther from the sun than the Earth, Mars is also bears traces of a different past. The temperature at the surface now, on average, is well below zero, -20 or so, and the total humidity of the Martian atmosphere amounts to a layer that, if it was deposited condensing on the surface, would be just something like 10 to 20 microns thick. So it's much more arid than the driest terrestrial desert, and it has a thin atmosphere made of CO2, which has a pressure at the surface which is less than 1% that of the Earth. So it's not really habitable as we think of it, as we think of habitability. But pictures taken from orbit and measurement of the mineralogy of the surface have demonstrated, like in this image, that water once was flowing on the surface of Mars, which was speaking of a very different climate. So you can see here the sinuous valleys that you can spot in this image, and the fact that one of those valleys opens in a crater which has a meteoric crater which has a very flat bottom, makes actually think that in fact that was a lake, for example, and the channel was a river, an emissary of the lake. So what happened on Mars? Now, if we extrapolate back in time and we compute, for example, the amount of water that was necessary to carve all those water-carved pictures of those features that were apparently produced by the action of liquid water, we can come with an estimate of the original quantity of water present at the surface of Mars, which is many times that what is present today. The only water existing today on the surface of Mars is actually frozen as ice in the polar caps. If the polar caps were molten, they would produce a liquid water, a quantity of liquid water that was uniformly distributed over the surface of the planet, would amount to a global equivalent layer, maybe 20 to 30 meters thick. If we were to compute the same measure on Earth by, for example, computing the volume of the water of the oceans and then dividing it by the surface of the Earth, the global equivalent layer would be thousands of meters. So nowadays, the amount of water present on Mars is a tiny fraction, less than 1% of the, let's say, quantity of water present on Earth. But the global equivalent layer in the path of Mars is estimated to be of the order of hundreds of meters. So maybe still much lower than the Earth, but significantly higher, perhaps an order of magnitude, perhaps even more than it is today. So what happened to Mars in the distant past? Now, what we know is that Mars does not have a global magnetic field. It probably existed in the past because we see remnants of magnetization in its crust, but it stopped early, probably because Mars is smaller and cooled more quickly, and this probably increased the viscosity of the mantle, stopping the motion of the nucleus and of the metallic nucleus, which produces the dynamo effect that maintains the magnetic field. So the loss of the magnetic field and the lower gravity combined to make it for a fast loss of the atmosphere of Mars. But apparently, if we extrapolate these loss mechanisms back in time, we would get that Mars had an atmosphere in the distant past that was made still of CO2 like it is today, but was much denser, perhaps as dense as ours today. And that would lead to an increased greenhouse effect that at this distance from the sun would be beneficial in maintaining temperature above the melting point of water. So Mars apparently was habitable because it had a denser atmosphere that produced a greenhouse effect, which was capable of keeping water liquid. And Mars also had a similar, very similar chemical composition to the Earth. So Mars apparently is a place where life could have been developing pretty much like it did on Earth. How long did the habitable phase of Mars last? Apparently, several hundred million years, which is of the same order of magnitude as the time in which life took to emerge on Earth. So Mars could be another roll of the die, another possibility for life to exist, and this is the key of the key reason why we are so interested in the exploration of Mars. Mars is a planet that could have been hosting life as we understand it, similar to that of the Earth, because it's developed in similar conditions. And so, since we do not know actually some key passages in the origin of life, how the complete set of steps that lead from an abiotic world to even the simplest living organism cannot be produced in the laboratory. We do not know what exactly happened. So studying Mars is trying to clarify if life would happen every time that there are the conditions for that to develop as we understand them, or if some fortuitous rare event needs to happen for life to develop. And this connects to the very fundamental questions of, are we alone in the universe? Is life so rare that we will never have a chance to meet it again elsewhere in the universe within the duration of our lifetime as a species, not as an individual, of course. So this is to mention that also Mars cooled down and volcanic activity spotted early, again because of the faster cooling of the planet and the thickening of the crust. And these are the polar caps where water, the surface water exists today. And so again, it's frozen, it's all frozen, it's not liquid. However, it's understood that Mars still has a residual heating in its interior, and much like the Earth, but probably lower. Anyway, by going down into the subsurface, temperature will eventually raise to the point above the melting point of water. So if we are looking for life that could still exist today, one has not to look on the surface where there could be only remnants of life, maybe fossils of microbiota or similar other creatures. But we need to dig deeper into the surface, and eventually we will reach the point in which any ice present in the ground would melt. Now, apparently, there is some indication that liquid water exists nowadays in the subsurface under the polar caps. So there's the possibility that an environment which could be considered a habitat exists on Mars today. However, this water would be kept liquid essentially by the thermal insulation provided by the ice, the kilometers of ice of the polar cap covering this specific area. This liquid water, in fact, was detected through the use of an ice-penetrating radar orbiting around Mars, which is similar to instruments used on Earth to look for subglacial lakes in Antarctica and Greenland. So this instrument detected echoes that were similar to those produced by subglacial lakes on Earth and interpreted these results as due to the presence of liquid water. Again, Mars is much colder than the Earth, and so this means that this liquid water remains liquid at temperatures that cannot be above 0 centigrade. It's too cold for even thermal insulation provided by the ice of the polar cap to bring temperature above 0. So apparently what would keep such water liquid is the presence of salts such as perchlorate and other salts, which would depress the freezing point of water. How is life capable of surviving in such heavily salted water? This is, of course, no one can tell for sure, but certainly it's not, even if it could be a habitat, it's a marginally habitable habitat for sure. Now, there is another indication that Mars could still host life today, and it's the presence of methane. Methane is being measured in very small quantities in the atmosphere, The detection still poses some problems in terms of repeatability of measurement. But methane cannot be produced on Mars by volcanic activity, which, as I mentioned before, has ceased. And so another possibility for methane, at least on Earth, the second main source of atmospheric methane is life. So even if there are other possibilities to explain this, the origin of the methane in the Martian atmosphere, let's say that this is one of the possible signs of life existing on Mars today. So if we were to look for life, how could we do it now that we think we have found that it's habitable and we have, let's say, indication that there could be life today? Now, the basic characteristics of life that most scientists agree upon is that life is based on the element of carbon, because carbon is the most chemically versatile, let's say, is capable of forming compounds with nearly every other element of the periodic table. And also it forms polymers, long chains of atoms, which are often the backbone of the complex molecules required by organic chemistry. Life requires liquid water, as I said before, as a solvent. There are other materials, other compounds that could be candidates for as a solvent, but liquid water is also liquid in the same range of temperature which carbon elements, let's say, chemical bonds are stable. So this is a useful combination of having carbon-bearing molecules being stable in liquid water. And there is a consensus in general that the chemical processes underlying metabolism is small. So you can, of course, it could be different in a different planet, but you would be able to recognize this sort of complex chemistry thanks to this and other characteristics like the one below. The energy for biological processes is primarily stored through phosphate bonds, and life probably will also select a kind of chemistry, biochemistry, which would be unitary for all life forms of a given planet. And DNA and RNA or molecules with similar properties would be also used to store genetic information and to become the blueprints for protein production and other complex molecule production. And perhaps in primitive, very primitive forms, there could be RNA, a single polymer for both functions. Life must be surrounded by a membrane, and membranes are more chemically stable than DNA and RNA, so they could be perhaps detected. And unfortunately, very simple organisms are very small, so if you are looking to find them, you need a very powerful microscope. And essentially, this is more controversial. Let's say that the criteria are listed in decreasing degree on consensus on their validity outside the Earth. Earthly life defines the limits of life in terms of physical parameters within which life can exist. Now, for the first time since the experiments carried by the Viking landers, which were landing on Mars in 1976 and attempted the detection of life by essentially taking samples of Martian soil and putting them in petri dishes and giving them heat and sugars to see if they develop some kind of metabolism. Now, the the first attempt at detecting life on Mars since then will take place hopefully in 2028 with the ExoMars rover mission. Of course, this is a European mission with a set of experiments aiming at detecting traces of life as defined by the previous criteria. And of course, there's a high probability they will find nothing, but it's in a different strategy than the one implemented by NASA. NASA is aiming for collecting samples and return them to Earth to perform all the complex analysis that cannot be brought to bear on a small rover on another so far away from home. So let's say the cost of the endeavor would be greater because you would send many rovers to collect samples, and then you need to send a spacecraft to collect the samples collected by the rover. But an early attempt, so the one by the European Space Agency, could be considered an early attempt, which admittedly would require some amount of luck to succeed, but certainly it has a merit. And anyway, moving away from Mars, there are other places in the solar system where the basic criteria for habitability exist. They are basically unknown from Earth because they have not been explored yet. But there are strong indications that at least the basic requirements of liquid water and sources of energy are satisfied, and the chemistry appears to be compatible, or let's say not so different that the basic elements for life would not be present, and sources of energy would not be present. One of them is Europa, which is the second Galilean moon orbiting around Jupiter. Its surface is crisscrossed by cracks because apparently beneath the icy crust, of course, Jupiter is 5 times more distant from the sun than is the Earth, and thus the surface of satellite orbit of moons of Jupiter is very cold. But under the ice, there should be liquid water, and that's what causes the cracks, the movement of liquid water, essentially. And this is the heating of the heat that keeps liquid water liquid on Europa is apparently produced by the tide, the huge tide that an immensely big planet like Jupiter exerts on Europa. So Europa is like a rubber ball being continuously squeezed by the tides of Jupiter, and this mechanical deformation, being also at the origins of cracks, disperses mechanical energy in the form of heat. And this is the heat that keeps water liquid under the surface. Also, the same kind of tidal stresses would keep the rocky core of Europa, which certainly exists because of the measurement of density that we have of Europa that tells us that the density of Europa is greater than that of only water ice, would keep this rocky core geologically active, and it would probably have a volcanic activity. So the black smoker that is shown on the right, which has been photographed at the bottom of the terrestrial sea, could well exist also on Europa. And since black smokers are considered a candidate site for the origin of life, Europa could well have all the conditions that are needed for life to emerge. Similar to, let's say, Europa, in the sense that it's an icy moon orbiting around a giant planet. This time it's Saturn. Is Titan. Titan is the 6th moon of Saturn. Is bigger than Europa, but it has this amazing feature that no other moon in the solar system has, of having an atmosphere. The atmosphere is also made by nitrogen, and surface pressure is 1.5 times that of the Earth. There's no oxygen, but there's a 1% of methane. And the combination of nitrogen, methane, and also part water vapor in the atmosphere is at the origin of a very complex chemistry initiated by the ultraviolet radiation emitted by the sun, which breaks down molecules in the Titan's atmosphere, like methane, and produces radicals that are capable of reacting with each other and produce longer chain of carbon. So producing basically a sort of prebiotic organic chemistry like pretty much existed in the Earth in the early times, and is replicated by experiments such the famous experiment by Uri Meyer. So Titan could have a complex organic chemistry by its own, even if it's so far away from the sun. Now, why is Titan appearing to be yellow? This is a haze produced exactly by those carbon compounds which condense and form droplets. So essentially, Titan is shrouded by smog, pretty much like our cities, or at least the largest one. Now, it has been found through the use of radar capable of looking through the dense coverage of clouds that there are lakes and seas on Titan, but they are not made of liquid water, of course. What they are made of, in all likelihood, is they consist of liquid methane and liquid ethane produced by the chemistry. So there's a solvent, there's carbon, there are complex or chemistry ongoing. Could there be life? This is a very, very puzzling question because, of course, it would be a very different life surviving at temperatures that is incredibly low for life to exist on Earth, yet still it could exist. And so it's very difficult at this stage to try to even imagine what kind of life could be there. There have been a few attempts of doing a numerical computer model of the chemistry, which is of the chemistry in Belgium in that environment at very low temperature, that would produce molecules that have an affinity, let's say, in this case, it would tend to form membranes such as those of the cellular of cells on Earth. Enceladus is also another moon of Saturn, in which we see geysers of spray, giant sprays of water being thrown into space. And this is again due probably to the tides of Saturn and hence by orbital resonances. But so Enceladus would be somehow similar to Europa, and in that it keeps at least partly molten ocean in the subsurface, but also it produces jets of water that carry the content of the ocean outside. So, the same probe that imaged the seas of Titan using radar, Cassini, which was operational between 2007 and 2017, was able to dive into those jets and make an analysis of the chemical composition of those jets. So, in addition to water, unfortunately, it did not have the capability to make a detailed chemical analysis, but it had a mass spectrometer. It detected several compounds that could be associated with chemical compounds. Also, the chemical outlook of the grains of silicate would be, the chemical composition appears to be compatible with the formation in a hydrothermal environment. So it seems that the plumes that we see at the surface of Enceladus originate from a volcanic activity in the rocky core of the satellite, which produce high temperature water jets in which dissolved salts condense when they enter contact with the colder oceanic water, and then they are transported through cracks in the shell, in the gaseous shell, and expelled into the void. So in the future, going there and collecting samples of those plumes with the capability to perform a detailed chemical analysis, especially for organic compounds, could reveal has the potential to reveal fundamental discoveries, to provide fundamental discoveries about the possible presence of life outside the Earth. Now, if we take the time to list again the habitability criteria for the bodies of the solar system, of course, the Earth satisfies all of them. Mars does not have liquid water on the surface, perhaps in the subsurface, does not have an environment which is stable for life because of the too thin atmosphere. But we see that Europa has satisfied by these criteria the same requirements of habitability as the Earth. Enceladus perhaps is not stable in the sense that the activity, geological activity that we see now could be only temporary. It would be, it's ephemeral and would not last in the future and did not exist in the past for reasons that unfortunately I don't have the time to explore. But other icy moons in the solar system, which I did not mention, have a similar structure as Enceladus and Europa. They have liquid water maintained, protected from freezing by an outer icy shell. Unfortunately, they also have ice I'm insulating those liquid layers from the interior, the rock interior, so they cannot communicate somehow with the rock interior in the way that Europa does through the volcanic activity that would inject in the ocean the chemicals that could be the basic fundamental bricks for life. So these sandwiched oceans, sandwiched between ice layers, could be completely sterile. And this is the case also for Titan. Titan does have interior ocean. So this is all that can be said at the time for the search for life in the solar system. There are candidates. There are places where we want to go with the capability to perform detailed chemical analysis and look for signs of life. We will do that in the future for Mars. We will bring samples from Mars to do that even in greater detail. One mission has been launched, and another one will be soon launched toward Europa to explore its subsurface through the use of radars. And Enceladus, for the time being, does not have a mission dedicated to it to explore its plumes. But in the future, we will ascertain and continue exploring the solar system for both for habitability and perhaps for the presence of life, hopefully. So this concludes my presentation. I suppose I could stop sharing here for the time being. And I hope I've not taken too much time. I hope there will be, maybe there's time for questions if you are interested.
Well, thank you very much, Roberto, for a fascinating talk and keeping absolutely perfectly to time, actually. We do have time for questions, so if people want to either raise their hands or speak to ask Roberto any questions. Roberto, there have been a couple of sort of false alarms as far as life on Mars are concerned. I remember when I was just graduated, I saw the Viking spacecraft had landed on Mars, and the first news item on the BBC News that day was about life is found on Mars, and that was either some strange chemistry or something was going on there. And the other one was about 20 years later was the Martian meteorite. Yeah. So I don't know whether you could say anything about both of those, just very briefly.
Yeah, very briefly. At the time, inside, it's easy to say that the experiments on the Viking probes were not the best choice for looking for life on Mars. But that's of course easy now with the 2020s InSight capability. At the time, let's say the sensation was made by the fact that adding liquid water to a sample of Martian soil caused a sudden release of gas. And but apparently the cause of that was a reaction of oxidation. As I mentioned, the atmosphere of Mars is very dry. Iron oxides are not the ones that form on Earth, and essentially it's iron-3 oxides. The state of oxidation, number of oxidation is 3, if I remember correctly. But adding water would cause those oxidation states to transition to 2 and would release oxygen. And that apparently is what happened there, because also the gas emission declined very quickly in time. So it appeared like life would have done differently with perhaps a sustained growth of gas emission. And so, but it's still open. The debate is still open. There are people that still claim that those results actually could not be explained only by inorganic chemistry, but I'm not really enough. I don't have enough competence to say much about that. So, but there's a literature. There's a group of people still working on that. And concerning the Martian meteorite ALH 86 something, I don't remember the whole number, but it was very interesting because it included inclusions and mineral grains of minerals that appear to be formed within living organisms, and it has been noted that many minerals that exist on Earth, and for example dolomite, would not exist without life. I mean, life, by creating chemical disequilibrium and going against the entropy, in a sense, allows the formation of minerals that would not exist naturally, and then are considered a sort of biomarkers, so tracers of the evidence of the presence of life, of the action of life. So, and there also were other evidence of mineralogical, morphological, chemical nature. Most of them were explained away, like perhaps contamination or alteration happening after the meteorite had landed on Earth. But no, I think that some of them still stand. And periodically, the group that studied them still produces a paper to make the case that those remaining features are still could not be explained by things happening on Earth, but still requiring life. But don't know the details.
Yeah. Oh, thank you very much for that very comprehensive answer, actually, and interesting to hear that the jury is still out in some senses. But yeah, thank you.
It's a minority, but yes.
Yeah. Yeah. Professor Medici.
No, thank you very much for the very interesting talk. I was interested in your suggestions about Venus and the possibility that there could be bacteria in the upper atmospheres. Would it only be bacteria, or there would be a chance for others, like maybe viruses, algae, and things like that?
Well,
yeah, that's really basically my question. Thank you.
It's difficult to me to answer this question because I'm not a biologist, and the evidence for the presence of phosphine itself is being debated. So, but there is a growing literature on this subject, and even if I'm not able to point to them to it very very precisely, I think you could reach to it by using basic keywords like Venus, phosphine, and this is all I can say, I'm afraid. I'm sorry about that.
Okay.
No, thank you. Thank you.
Do we have more questions?
There's a hand.
Oh, sorry. Okay, yeah.
Hi.
Hi.
This might be a very cliche question, but I wanted to know, Mr. Roberto, what got you into this career? Was it a quiet curiosity from when you're younger, or was it something that you discovered as you got older?
Well, some months ago, I was just making some room in the garage, and I saw some of the books that I had as a child, and they were already talking about space exploration. So I think I never had a real choice about choosing what I like since a very early age. And it began with science fiction, but then it developed. I must say also, however, that was not really always easy, in the sense that when I told my parents I wanted to study astronomy, they were not particularly happy about that. But that's another part of the story. I convinced them that I could have changed to engineering very easily because the exams were very similar. So I managed to get enrolled into physics, and then luckily I could finish my studies.
Yeah, good question. You have more? Could you tell us a little bit more about? Oh, yeah, Dr. Schipper. Yeah.
Thank you, Prof. Thank you very much, Dr. Orosei, for the wonderful talk.
I hope I am clearly audible.
You are.
Thank you very much. You know, I have two points. The first one is, you know, when you were talking of the optimal habitable zones for different for the different planets. Actually, for the solar system, and then you put the different planets there. It was based on water. So I could imagine we as you mentioned, we could also have other solvents. So the habitable zones for other solvents, I imagine would be at a different radial positions with a different radial widths, depending on the solvent. I would like your comments on that one. And the last one would be, you know, we have students, some from secondary, some from university, who are present, and I don't know if you have some words of encouragement and also advice in terms of courses and stuff like that that you can offer. Thank you very much for the wonderful talk.
Thank you. Thank you very much. Well, in the same, only a few slides after presenting the habitable zone, the concept of the habitable zone, I was presenting also bodies which exist outside the habitable zone and that possess liquid water and probably all the requirements for habitability like Europa. So the habitable zone is a rather vague notion at this point. It's true that if you stick to the idea that water is the best solvent for life in some way, then the habitable zone still makes sense for planets in which water is present at the surface. So in general, as new planets are discovered around other stars, and sometimes the press announces the discovery of another Earth-like planet, the twin planet of the Earth, and so forth. And this is always based on the fact that the planet appears to have a size similar to that of the Earth, a density similar to that of the Earth, and so similar composition, rocky with metallic nucleus, and the distance from the star, which is compatible with the temperatures necessary to keep water liquid. So it's true, the habitable zone is the basic, it's just a basic yardstick to assess the fundamental requirements for life in another planet. But it's not really the end of it. I mean, there are many other ways. It's true also that no organism using a solvent which is different from water has been found. But it's also true that giant planets exist. They are very common in the universe. So perhaps the most common type of habitable body outside the solar system could not be planets like the Earth, terrestrial planets, but perhaps icy moons around giant planets. This is the big, and in fact, the current, let's say, edge of research in studying exoplanets, planets around other stars, is the search for moons around giant planets, which of course are much smaller than the planets themselves, and so they are very difficult to detect. Concerning students, as I said, getting to study astronomy sometimes does not meet the approval of your family in some cases, but there are many other ways in which people can work in space exploration, of course. And engineering, which is both mechanical, electronic, aerospace, biology for the study of the possible candidate for life outside the Earth, and chemists and geologists. So there are, in fact, planetary science and the search for life outside the solar system, the astrobiology outside the Earth, field called astrobiology, is an extremely interdisciplinary field in which people can come from many different paths of life, from many different disciplines, and work together. So let's say there are many opportunities. The important thing is to get some connection with people already doing this kind of research in your field. But it's possible to become a chemist and study other planets. This is for sure, and biology and so forth.
Okay.
Oh, splendid. Splendid. Thank you very much.
Okay. If we have no more questions, I think I'd just like to thank, Bill Tomlinson. Yeah, Bill, do you want to ask you a question?
Thank you, Robert, for your presentation. I just had a quick one. I keep reading so much about, well, the new moons that they're discovering, Saturn and Jupiter, and what properties and characteristics those moons now seem to be giving us a glimpse of. If you were the director at NASA and were planning the next mission to go off in search of possible life forms within the solar system, as I don't think NASA has any nearby plans for leaving the solar system, where would it be?
Well, actually, NASA, if I were the director of NASA, I would probably ask the advice of many other specialists, not only by my own. I wouldn't decide by my own, which is actually what NASA does. There are working groups writing thick papers on what to do next to achieve the goals that have been established as the main goals for NASA. And of course, the search for life in the solar system is on top of the list. And the current strategy actually has a marked dichotomy, the split. There is Mars, and then there is the rest of the solar system. So Mars is getting much of the attention, and the best efforts to get there and bring back samples are now being developed, not only as a strategy for NASA, but also at an international level. In happier times, maybe 10 years, 15 years ago, those plans involved the participation also from Russia and China and Japan. Now, the main partners in this endeavor remain the European Space Agency and Japan, with perhaps Canada and other minor agencies. But the idea, the plan, the strategy is to focus on sample return. So in the next decade, I mean, already by perhaps the end of this decade, the plan is to have a mission that will be capable of landing on Mars, collecting the sample caches prepared by different rovers, and then fly back to an orbiter waiting for the caches and that will bring them to Earth. So this is the main goal. And the next goal in the 30s, 40s would be human exploration, of course. And although this is not strictly connected to the search of life, at least in my view. Then there is the outer solar system. Venus is, and the rest of the solar system, Venus is a relatively recent finding. So people were starting to realize that Venus had a different climate and perhaps oceans, but it's the phosphine thing that started an interest. And in the coming years, I think within this decade, there would be at least 3 missions flown to Venus, 2 from NASA and 1 from the European Space Agency. But the characterization of Venus is still in its early phases, so it will be mostly about geology, about chemistry of the atmosphere, so to characterize the environment and try to reconstruct the geological and climatic evolution of the planet in greater detail. Then the search of life will continue if phosphine will be confirmed if other evidence is found for life. Icy moon are the next other big target. So icy moon are very technically challenging, of course, because they are covered by layers of ice which are kilometers thick, perhaps in some cases tens of kilometers. So there's no hope to getting into those oceans anytime soon, but they are in the crosshair, and eventually some way will be found. Of course, the most accessible environments for the search of life are Enceladus and Titan. So there will be there are currently no plans for a mission to Enceladus, although there are several studies and proposals to do that, how to do that. And but there's already a mission to be being developed to land an airship on or a boat, actually, no, more likely a boat on the lakes of Titan. And it's called Dragonfly, I think. So I think it's already in the developing phase. I haven't been hearing much lately, but the coming years, probably it will take more than a decade to get there. I mean, before anything lands on Titan, it will be more than 10 years, more like 15. Well, we certainly bring very interesting news.
Promises to be a very interesting next few decades.
Yes, let's try to survive until then.
Yeah.
That's right. Thank you.
Thank you. Thank you.
Okay, I think we will have to wrap up now. Some great questions and a great talk again. Thanks ever so much, Roberto, for taking the time and trouble to give this talk. And I think it will cause a lot of discussion among everybody afterwards, which is always the sign of a very good talk, good speaker. And we have our next talk will probably be in about a month's time. I see Guillaume's here now on the screen. Perhaps Guillaume will actually will send details around to everybody about that. But in the meantime, I'd like to thank you again and say good evening from Liverpool in the UK to Italy to South Africa and to Botswana and several other places as well. I'll see some of you again in a minute. We have a committee meeting, but on a Zoom link this time, which hopefully will work. So thanks again.
Roberto, thank you very much for this splendid presentation. Thank you very much.
Thank you. Thank you so much.
Thank you.
Goodbye.
Bye. Bye, everybody.
Bye.
Wonderful talk.